All right, so we're going to start our next unit, and so far we've been talking about all sorts of just different kinds of motion, like linear motion, and we made connections with momentum and energy. And now we're going to do a little bit of a transition and focus a little bit more deeply into rotation. Okay, so before we do that, I just want to kind of contrast two kinds of motion. So we can have motion which is translational, okay, and this is mostly what we've dealt with so far. So if we have an object somewhere on a number line, it has translational motion as it moves along, okay, in that one or two dimensional space. And it's just the idea that it's moving kind of in a straight line, okay, and that the direction is going to be changing, but generally we can say translational motion is when things are moving straight. And then on the other hand, we have rotation, and that's where we're going to be focusing on this chapter, okay? And then in the next chapter, we're actually going to put the two together and have scenarios like when things are rolling. But really, right now, we're going to focus on rotation. And the variables that we used for translation, we talked about position, displacement, velocity, we had average velocity, acceleration, and average acceleration. All of these things also exist in a rotational sense. And so we're going to kind of go through and talk about all of those rotational variables and talk about how we measure them. All right, so if you look over here, you'll see kind of our list of translational variables. I included time at the bottom. It's definitely not a vector, and so certainly not limited to translational discussions, but I put that because these are kind of all the different variables we use. And I listed velocity and average velocity and so on. So let's go ahead and look at some of our analogs. So instead of talking about linear position, we can talk about angular position. Our symbol for angular position is theta. So just like we can have a position on a number line, we can have a position, okay, in a circle, and we would measure that position by saying what the angle is, okay? And so that represents the angular position. Now, let's say the angular position changed. So actually, before we continue, angular position can be measured in degrees, okay, or radians. In this chapter, we're going to be focusing on radians, okay? Occasionally we'll talk about degrees, but our focus will be in radians, okay? And so I'll put right here, this is measured in radians, okay? Okay, so let's say that, well, let's go back to translation. So if you had started, say, at this position, we'll call it x1, and you went to some other position, x2, if you subtract those, x2 minus x1, that would give you displacement, okay? Well, the same thing happens here. Let's call this theta 1, and let's say we move to some new angular position, which we'll call theta 2. Well, theta 2 minus theta 1 is our angular displacement, okay? It kind of represents a similar thing to linear displacement. It tells us what our change in angular position was, okay? So that's our angular displacement. All right, and when that displacement happens, it's going to happen in some certain amount of time, okay? And so when we talk about that, how fast it was moving, that's our angular velocity. The symbol for angular velocity is omega, and we can have instantaneous angular velocity, or we can have average angular velocity, okay? And let's say that something is spinning, it has some angular velocity, and that angular velocity increases. Well, that would be a change in angular velocity, which we'll call angular acceleration, and we'll use this symbol alpha for angular acceleration. Just like we can have instantaneous angular acceleration, we can have average angular acceleration. And so these represent all of our angular values, okay? And the last thing I want to mention is this. So on our number line, the convention for positive and negative is that positive is to the right and negative is to the left. We have a similar convention with rotation, and it's this. If you're rotating counterclockwise, that's positive. If you're rotating clockwise, that would be negative, okay? And just kind of an easy way to remember that is that clocks, and you see this in the book, clocks are negative, okay? And so we'll talk more about this convention later, but just for now, just know that counterclockwise positive, clockwise negative. And this is a convention. It's not, it is, if we stick to this, it's going to simplify a lot of stuff for us later, especially when we get to more complicated discussions of rotation. So this is a good kind of practice to stick with. Okay, so the next part of our discussion here, we're going to take a look at radians. Okay, so radians are a really, really important tool for physics. It's probably something you learn about in, I'm going to say maybe pre-cal. I'm not sure when you learn that now. But it's something that, at least in my experience, when I learned it in high school, no one really explained to me what the purpose of radians were. They were just another way of measuring angles that was really, I felt pretty annoying because I didn't really understand it. And it wasn't until I started to study physics in college that I really understood why radians are so important. And the reason why they're important is because it connects whatever your angle with to the amount of distance you've traveled along the circle. If you know your angle and you know your radius, you know your angle in radians and your radius, you can find your distance, and we'll call it S, your distance S around the circle, because the definition of a radian is that it's the angle for which the arc of the circle has a distance equal to the radius. And so we say that the distance is equal to the radius times the number of radians. Okay? Now, on the surface, this might be really confusing to you. And so I have a couple of illustrations I want to show you about how this works. Okay, so now I'm going to show you an animation that's going to kind of show basically where a radian comes from. So if we measure out a certain distance along a circle, okay, for which the arc here is the same length as the radius. Let me show that again. So watch the radius kind of get rotated and bent until it fits that distance. Okay? Well, when you can take the radius and bend it around and make it that distance, this angle then is equal to 1 radian. Okay, let me show that one more time. Alright, we can take the radius, bend it up here, and that makes 1 radian. Okay? Now, if we take that 1 radian and move it around the circle, okay, that's 1, 2, 3, 4, we can fit 5, 6, and we have a little bit extra room, and what you'll find out is, if you were to measure it yourself, you would get about 6.28 radians around the circle, okay, and this is just a fact about circles, that the radius of a circle can fit around the circle 6.28 times, or fit around half the circle 3.14 times. Okay, and this is actually where we get the value for pi, just from this relationship. Okay, so there's one more thing I want to show you. This is just another illustration animation. This one I pulled from Wikipedia. I think it's also really helpful. So I'm going to show it real quick, and then we will wrap up this video. So here we have a circle. We're making a circle with that radius r, the length of that red line, and we're going to trace that distance along the edge of the circle, and that angle represents 1 radian because it has a, it has right here, that distance was 1 radius, and so you have 1, 2, 3.14 or pi radians in this half circle. And then for the full circle, it's going to be 2 pi radians. Okay?